Afternoon. We're about to do geometry. Anybody out there for geo right now? Anybody geo in the chat? Nobody's geo in the chat. Okay, well, we'll still get started anyway. So that way the replay is available. You know how it is. So, go ahead and switch it over and let's rock and roll. Gonna turn just a wee bit more. All right. So, right about here is the start of the geometry notes. Welcome, welcome. It's Sunday, October 4th. We are doing the 3.3 notes. It's another transformation. We've seen reflection, which was the act of flipping. We've seen translation, which was the act of shifting around. And now we're going to see rotation, which is the act of turning the object. So I think we're all pretty familiar with the idea of rotating an object, but it's not just, we're not just going to casually turn it. We're rotating it like a specific number of degrees, or rotating it around a specific point. Okay? So we've seen that reflections and translations are two types of rigid motions. Rigid, again, meaning that, anytime we shifted an object or reflected an object, it was still the same shape, still the same size. You could clearly see that the objects were twins, so to speak. Same with the rotation, right? When this guy gets rotated 120 degrees, it still looks like the same shape. It is still the same shape, just in a different spot, just in a different position. So it's a rigid motion because things are staying the same. So a rotation turns all points of the plane around a point called the, let's switch it up, let's do blue, center of rotation, which is this guy right here. You can see we're turning around that specific point, that point that we're rotating around, right? You can see my fingers going around my fist here. We're rotating about this point. That's the center of rotation. And the angle of rotation states the number of degrees through which the point rotates around the center. So this right here is the angle of rotation. The figure to the right shows a 120 degree counterclockwise rotation around point P. Counterclockwise, a clock ticks going this way, right? We're going around a clock this way. 1, 2, 3, right? Counterclockwise is the other way around, okay? Get rid of that. So when no direction is specified, you can assume the rotation is in the counterclockwise direction. That's pretty big right there, right? There's a big difference between turning 90 degrees this way as opposed to 90 degrees that way, right? There's a big difference between the two. So we're going to safely assume that if it doesn't tell us, we're assuming counterclockwise, okay? And once again, there is this function notation for our transformation. So we've seen a little r for reflection. We've seen a capital T for translation. Today we're seeing a capital R for rotation. So the big R tells us, okay, we're rotating. Gotcha. What are we rotating? Or what object are we rotating? This point, right? We're rotating point A. Okay. How many degrees would you like me to rotate it? M. And where would you like me to rotate it around? Point P, right? Because there's this center of rotation that we're going around. There's a difference between rotating it, like if I were to draw an object, right? Oops, I wanted it to click into place. If I were to draw that object, there's a difference between rotating it like so, like sort of just rotating it in place, right? Versus taking it and rotating it around like so, like going around, say, this point right here, right? There's a difference between rotating it around itself versus rotating it around a specific point. So our capital R here, of course, stands for rotation. The point P stands for the center of rotation. And the M represents the angle of rotation. So in class, if we were in person, we'd be able to do this pretty fun thing with tracing paper to simulate a rotation. But I'm going to try to do my best here with this app that I have. So we've got this here, and then I'm going to draw this shape. All right, there's that. I'm going to pick these guys up here and watch how I can rotate it. You see how the line is staying on point P? You see how the line's staying on point P? So 150 degrees, what is that angle that we're making? Well, what we'd be measuring is this angle right here. I just moved it from where it was to now over here. So here's A prime, here's B prime, and here's C prime. And we just created roughly 150 degree angle. That's the rotation that's occurring. That's what this is saying right here. Okay, so we'd be able to do it pretty fun with some tracing paper, but that's just not going to happen. So I'm kind of simulating it there for you. Okay, so when we're talking about the angle measure, we're talking about this, because this is the starting position, this is the ending position, and the difference between the two is what we care about. That's the angle measure. And again, like I said, you can rotate it about any point, right? This is point P right here, but what if I took it and rotated it about this point? What if this is our new point of rotation, and I'll call this Q? Well, now we're taking this shape. Whoa, that's interesting looking, isn't it? And we're rotating it. And what would that look like? Let's have a look. Well, now as I rotate it, it would be turning like, oops. Oh, that's difficult. You see how difficult that is? Turn. There we go. That's our rotation now, like so. So it's different. All right. It's still a rotation, but oh, now we're rotating about point Q. So depending on where your point of rotation is, clearly the object's going to go in a different spot. Okay. So the table provides coordinate notation for counterclockwise rotations in a coordinate plane. You can assume that all rotations in a coordinate plane are rotations about the origin. Also note that a 270 degree rotation is equivalent to turning 3/4 of a complete circle. So we had rules for reflections. Do you recall? Our reflection rules were something like, okay, if you're reflecting across the line y equals 0, your xy point is going to become, what would that become? X comma negative y, okay? And if you reflect it across x equals 0, then that would become negative x y. You recall those rules? And we were using them pretty regularly. Well, now there's a new set of rules for rotations. And I would encourage you, to have this open as we do the classwork, just to have these handy. So we are rotating 270 degrees. So, okay, we're rotating about the origin 270 degrees. So, like I said up here, it matters where point P and point Q are. Well, we're rotating about the origin, which is right here in the center. Okay, so that's our point of rotation. And we're rotating this figure 270 degrees. Well, what's the rule for 270 degrees? It's right there. So these coordinates are transforming like so. Okay? So let's try to do this. What's happening? X and Y are switching, because now it goes YX, but also the X becomes negative. Let's say that again. X and Y are switching, right? Because you can see the Y came first and then the X. But also, the X got flipped. It has the negative on it. So when I look at this point, I'm flipping it to be 1, 3. But also, the X value gets flipped. So 1, negative 3. I look at this, and they get flipped. So 2, 4. But the X value changes signs to 2, negative 4. If you need to write an in-between step, you can think to yourself, okay, these guys are flipping. All right, now what? They flipped, but I also need to make a negative on that. So 4, negative 1. I look at this and they flip to 2, 0, but you can't really change the sign of 0, so it's going to stay the same. Okay, so let's plot those 4 points, right? Let's plot these 4 points. So we've got 1, negative 3, 2, I went negative 1, that's my bad. 1, negative 3, 2, negative 4, 4, 1, 2, 3, negative 1, and 2, 0. So this is A prime, B prime, C prime, D prime. Looks like there was no D on that. There we go. Whoops. I guess I can't do that because it's going to make it a perfect shape, isn't it? There we go. So you can see here, hopefully you can see here how, okay, we rotated 270 degrees. And how so? How did we rotate 270 degrees? So this object, right, is turning. Oh, what just happened there? Turning. This is hard. Don't blame me. Turning. Right? And boom. Hopefully you see my point. Do you see what I'm getting at? How it's rotating, going all the way around. So it's starting. I mean, we'll just get rid of it, right? Let's be honest. We don't need that anymore. So it started up here. And this point twirled around. And this point twirled around, right? That's my 270 degree rotation. Let's do it again. This time it says to rotate 180 degrees around the origin. And what's the rule for that? It says to simply swap the signs. So xy becomes negative x, negative y. So that means instead of negative 1, 1, we now have 1, negative 1. Again, this doesn't just mean put a negative on it. That's not what that means. It means take the negative. So when you take the negative of a negative, it now becomes positive. And when you take the negative of the positive, well, it's going to go negative. So this is going to be positive 3, negative 1, positive 3, negative 4. I'm just following those rules, applying the rule, and let's see where it takes me. 1, negative 1, there's A prime. 3, negative 1, there's B prime. Oh, he subbed again. Food SJK with the sub again. Thank you, sir. Or ma'am. I actually don't really know who you are. And 3, negative 4. 1, 2, 3. 1, 2, 3, 4. Thank you. I appreciate it. I really do. That's awesome. And there's that. So hopefully, I think that one's a bit more obvious that it was a rotation. And I'll try my best again to go take this object and, twirl it around the origin, right? You can see it. I hope you get the point as to what I'm trying to show you here, that it's twirling around and going to rotate, right? I hope that is coming across as best as I can there. Let's do it again, one more time, one more rule. 90 degrees says xy and then negative yx. So it's similar to the first one, except instead of switching the sign of the x value, we're switching the sign of the y value. So I've got negative 1, 1. So they're switching places. So again, let me do it like halfway. They're switching places, 1, negative 1. They switch places, but then the y value gets negatived. So you switch the sign. So now it's negative 1, negative 1. X is still staying negative. No one said to change the sign. So when it switched and went here, right, it's going to be negative 1, and it's going to stay negative 1. All right. With this guy, they're switching places, so 0, 3. And then the y value becomes negative, but again, you can't really make 0 negative, so it's going to stay put. And then this last one, they switch places and becomes 3, 0, but the y value gets a negative, so negative 3, 0. So my 3 points are at negative 1, A prime, 0, 3, 1, 2, 3, which is B prime, and C is at negative 3, 0, so right there, C prime. And I think that one's also kind of clear that it rotated. It rotated. It's a little bit of a tighter turn, right? Because it's closer to the origin already, right? But you can kind of see that right there. I feel like that it's rotating. And then this is just a few more for practice. But what we don't have here is the points, right? What was nice about this is that we had a table made for you in advance with the points, and then you just applied the rule. Well, now we have to look at the graph and see what the 3 points are. So these 3 points are, you can see here y is at 3, 3, b is at 1, 1, and e is at 5, 1. Not that much work, right? We now have the points, and now let's apply the rule. Well, which rule do we use? It says 90 degrees. So I go back up here. Which one's the 90 degrees? This guy right here. So xy becomes negative yx. So that's the one that we just used. That's the one that we just used. So again, you're switching places and you change the sign of the y value. So 1, 1 switches to 1, 1, and then the y value becomes negative. So if you need to make a table off to the side, then so be it. 1, 1 becomes 1, 1, and the y value here gets a negative. So negative 1, 1. So it goes right there now. B prime. 3, 3 switches to 3, 3. Kind of lame. That's okay. They switch place to 3, 3, but the y value gets a negative on it. So negative 3, 1, 2, 3, up 3. So there's y prime. And then E, 5, 1. So the y value gets a negative on it. That might be nice to do first. You're like, okay, the y value is going to change signs. So instead of positive 1, it's a negative 1. So 5, negative 1, and then switch. Negative 1, 5. Which is all the way up there. E prime. I don't know why that didn't click. As long as you can follow those rules up there, I don't think it's too terribly difficult. 270 xy to y negative x. Right? I see, oh, we're rotating 270 degrees. So I'll scroll up here and look at the 270 degree rule. Xy to y negative x. So the x value changes signs and they switch places. What do we just do? The y value changed signs and we switch places. So now the x value changes sign and they switch places. So again, I'll label these for us. We've got this point, and this point. So this is at, oops, y is at 1, 2, and j is at 3, 2, and d is at 1, 4. So when we apply the rule, where should we start? Let's start at d. So 1, 4, the x changes signs, so it's a negative 1 now, and they switch places. So 4, negative 1. Let's get in a rhythm before I start plotting. Let's do it again. The x value changes signs, because that's what I see here, right? I'm just looking at what I see here. I'm not just pulling this out of thin air. I see, oh, the x value is changing signs. It has that negative on it. And, oh, the y came first, so they switched places. So 1, negative 2 becomes 2, negative 1. And 3, 2, the x value changes signs and the points switch places. So that becomes a negative 3. Switch places, 2, negative 3. And let's plot. So 4, 1, 2, 3, 4, down 1, 2, down 1. This was d prime, by the way. This is y prime, by the way. And j prime, 2, down 3. There's j prime. Beautiful. And you can kind of I would encourage you to sort of take an educated guess as to where, I should have done this beforehand, that's my bad. But I would encourage you to go okay, if I'm rotating 90 degrees, that's a quarter of the way around. Here's an entire circle. So a quarter of the way around would be around here, and halfway would be over here, and 3/4 would be over here, and all the way back around would be where it started. So when you see 90 degrees, you know it has to end up over here somewhere. If you end up with a shape that's halfway in between or clear over here, that doesn't make any sense. So again, thinking about this with 270, here is our full circle. 90%, or sorry, 90 degrees, 180 degrees, all the way around, 270 degrees, 3/4 of the way, and then 360 all the way around. So we know that this kind of makes sense, you know? All right, let's put it together and combine what we know. Let's combine what we know. Let's take our sweet time here. This is a great review of all transformations. This is a great review of all of our transformations that we've learned thus far. So the first thing says rotate it 180 degrees. Let's go back up and get that rule one more time. That's xy to negative x, negative y. So when I look at this triangle, I've got, where are our points? 1, 2, 1, 2, 3, 4, 5. So M is at 2, 5. F is at 2, 1. And R, 3, 4, 5, is at 5, 2. And I apply this rule, which simply says change the signs of those 2 points. So your 2, 5 becomes, where's a good, here, I'm going to do it down here. If you have these printed, I say do it on the back. So 2, 5, and again, here's the rule. I'll write it again so we can see it. Negative x, negative y, so the signs just switch. So we just rotated. Yeah? I don't know. Why did I just do that? I don't know why I just did that. Rotation of 180 degrees. That's what we just did. And we'll do it to each of these points. So we've got 2, 5, 2, 1. And this is an easy rule to apply, right? Literally just switch the signs. You don't have to think about switching. That one's an easy one to apply. So now let's plot those. Let's plot these guys. Negative 2, 1, 2, 3, 4. Negative 5. So that's M prime. Because, how do I know that's M? Because I went M, F, R here. So that's, the first one's M prime. Negative 2, negative 1, that's F prime. And negative 1, 2, 3, 4, 5, negative 2 is R prime. Didn't click. Let's try that again. It hates me. Let's try that one more time. Perfect. Okay. So there's that triangle. And then the follow-up step is to reflect it across the line y equals negative 1. Remember, y equals is a horizontal line. So here is the line y equals negative 1. And when we reflect it, everything's got to be symmetrical. So F here is, or sorry, R is 1 away. So it's got to be 1 away on the other side. F is right on it, so it's going to stay put. And M is 1, 2, 3, 4 away, so it's going to be 1, 2, 3, 4 away on the other side. So let's bring that to life. So our double prime, F stays put. 1, 2, 3, 4. 1, 2, 3. M double prime. Beautiful. And you know what? Just for fun, I'll leave this one blank for class. I have one extra one to do during class. So as you wrap up that problem, people watching live or watching the replay, a reminder that our quarter's about to end. Everything's due. Our 3.1, 3.2, the C-Day quiz, all of that. That's all going to be wrapped up and be in the quarter grade. Thank you for watching. I appreciate you for getting this far. I appreciate you for taking notes with me. Yeah, I really don't have much else to say. All right, so I don't know if anyone's still watching me live right now. However, I'm gonna go post in Algebra 2 now. Anybody hear Algebra 2 yet? Okay, so I'm going to turn down the music just a little bit more. Alrighty, so Algebra 2 notes starting right about here. Welcome. It's October 4th, Sunday. We are looking at the last set of notes from Unit 2. We're looking at Lesson 7. We're looking at quadratic inequalities. So we've seen inequalities before in Unit 1. And yeah, we're just looking at inequalities, except in relation to quadratic equations, as opposed to what we were looking at before, which was like lines and number lines. And don't worry, though. Desmos can handle quadratic inequalities as well. So that will make life a little easier here, so we don't have to do any crazy drawing. Let's take a look at this, though. So this quadratic equation has already been plotted. Yeah? This has already been plotted right here. So if this were an equal sign, okay, it would literally only be the graph. But we're not saying that it is just the graph. We're saying that the y values are less than, which is why the underneath has been shaded. This underneath, we just started our algebra 2.7. This underneath portion is less than, right? Because that's what this says, less than. So to be under, so the shaded region is underneath, so that's less. We would have shaded the above region if it were greater, okay? So shaded below, that means less. Shaded above, that means greater, okay? So that's I think that's pretty straightforward, because less means to be underneath, right? If you have less money than them, your dollar amount's going to be underneath, right? You know, and if you are, less worthy, right? You're small, you're being, overcome by, the more strong, powerful person or whatever. Less means underneath, okay? So where are the zeros of this graph? Right here and right here. So the zeros are at 1, 0, and 4, 0. Are the x-intercept points on the parabola solutions? So it says, wait, let me take a step back. That phrasing there. Are the x-intercept points on the parabola solutions? Well, we don't have an, I don't like that question right now. I'm ignoring that question right now. I think these questions are out of order. I think this question should have came first. Yeah, I think my logic there. Sorry. So we know that these are so let's take a step back. I don't want you to be confused just because I was kind of fumbling my words. These are clearly the zeros, okay? We know that those are the zeros. We're used to that. We know that's where the graph crosses the x-axis. Plenty of us have been finding solutions for the past 4 lessons using Desmos, knowing how to do that. Awesome. So instead of simply writing y is less than, what if we wrote 0 is less than x squared minus 5x plus 4? Well, let's think about 0 equals x squared minus 5x plus 4 versus 0 is less than x squared minus 5x plus 4. Let's think about those two things. This is saying, where does the graph literally equal 0? It equals 0 right where those zeros are. That's where it's equal to 0. But that's not what we're asking. We're asking, where is the graph less than 0? The graph is less than 0 down here, right? This is the less than 0 area. right? So where is the graph less than 0? Specifically, here. This part of the graph is greater than 0 because it's above. This part of the graph down here is less than 0 because it's below. You see the difference there? It's the above graph is greater than 0 because it's above 0. The part below is less than 0 because it's below 0. So it's asking, are the x-intercept points a part of the solution? The answer is no. That's where the graph equals 0. We want less than 0. So I would have open circles right there. Does that make sense? We'll do this a few times, but I hope that makes some sense. Look at the graph and go, okay, my graph is 10 here, it's 5 here, it's 3 here, it's 2 here, it's 1 here, it's 0 here. Where is it less than 0? It's less than 0 down here. That's where it's less than 0. And that's where it's equal to 0. And that's where it's greater than 0 because now it's above. So when we ask ourselves, where is the solution for this equation right here? It doesn't include this point, so it's an open circle, less than 0, less than 0, less than 0, getting a little bit bigger, and then equal to 0. Don't count that part, so an open circle. So use the reflexive property to write the inequality. Use the reflexive property. I don't want to do that. What is the solution set? Our solution set is from 1 to 4. So we're not including 1 and we're not including 4. Or you could write it as like that. So x is between this part of the graph between 1 and 4 is our solution. Wait, did I just do that backwards? Oh, I'm embarrassed. Gosh, why do I always... Should I just restart? Should I just have a fresh start on this? Barely anyone's watching right now. I'm going to have a fresh start on this. I completely misspoke and misread this. I completely misread this. I'm completely restarting. If you guys who are watching live, the small handful, I'm completely restarting. And right here is the start of the Algebra 2 notes. So we're looking at quadratic inequalities. I'm restarting. Here we go. So I don't like the order of these questions. I want to change these for next time. But let's just say, I'm not feeling it right now. Okay, so we're looking at quadratic inequalities. We've seen quadratics, we've seen inequalities. Let's look at this here as a quadratic inequality. If this was an equal sign, that would simply be the graph, okay? I wouldn't have any of this shading, okay? But the second I introduce this inequality symbol, all of a sudden I have to shade. What we're talking about is here's the graph, and we're saying y is less than the graph. So that's all of this stuff. Less than means below, greater than means above. Well, what if we had an equation? So I'm going to do this one first. What if we had an equation that we needed to solve? Because this just says graph. But what if we wanted to solve this equation for x? So instead of an equal sign, it's a less than sign. And what if we wanted to solve this? Well, this says 0 is less than this. Less than the graph. Or another way to think of it is if we do this step, use the reflexive property to write this in another way. X squared minus 5x plus 4 is greater than 0. And looking at it this way has opened my eyes a little bit right now. I don't know if it's opened your eyes a little bit, but what does this say? This equation says the graph is greater than 0. So we want to know, where is the graph greater than 0? I'm repeating this portion. Those of you watching live, and whether you're watching the replay, I'm doing this over again. I'm repeating this portion because I misread it, right? So I have a graph greater than 0. So the solutions to this equation are greater than 0. So take a look at our graph. Take a look at our graph. Here it is. Here's 0. And we want to know, where is our graph greater than 0? Well, this half down here is less than 0, and these arms right here are greater than 0. That's the proper solution. That's my bad for misreading. So don't forget about the zeros, though. The zeros are at, so let's do this third, 1, 0, and 4, 0. So if this equation said equal to 0, well, those 2 points would be the solution, of course, right? We've done that a million times, right? We've solved equation like this a million times, and we've all just plugged it into Desmos and took a look at the intersections, okay? That's easy. We're talking about not just where is it equal, but where is it greater than 0. The graph is greater than 0 up here. So when we plug these guys in, it's equal to 0, not greater. So are these solutions? No. That's equal to 0. We want greater than 0. So these two arms, as x gets really negative, our graph gets really big, all the way up until 1. And then on the other side, from 4 all the way up to infinity as it gets bigger on the other side. All right, I did that much better now. Let's try it again. So, I like this as step 1. Write the given quadratic inequality substituting y equals 0. So we have 0 is greater than or equal to x squared minus 2x minus 3. Let's take this and use the reflexive property. We can say x squared minus 2x minus 3 is less than or equal to 0. This is saying 0 is greater than this. I'm just flipping it around and saying this is less than 0. It says the same thing. These guys say the same thing, just one's written first. Okay? So, my logic that I was using when I messed up is now this is going to make sense now. So, when is our graph less than 0? Well, again, here's the graph. and here's 0. Where is our graph less than or equal to 0? This part down here is less than 0, and these two arms are greater than 0. And we're also saying equal to. Well, it's equal to 0 at the zeros, of course. At the zeros, our graph is equal to 0. That's pretty obvious, I think, at this point. So these are also a part of our solution this time. So the zeros are at -1, 0 and 3, 0. Yes, they are. So our solution set can be represented by, we're including -1. So we're saying -1 all the way down and around up to 3. Boom. So let's plot this with Desmos. I don't want to drain ourselves too much trying to graph this by hand. So I've said in the past, and plenty of us have been doing this, plot one side of the graph, plot the other side of the graph, and see where they intersect. I've said that many a time when using Desmos, and here you go. There's that. So when I look at this, here's the points of intersection, okay? Those would be the solutions if our equation said equals, but it doesn't. It says less than or equal to. And again, we can flip this on its head and write it like so. I'm flipping the sides of the equation and flipping the direction of the symbol, and they say the same thing. This says the same thing as this. To say 0 is less than this is the same thing as saying this is greater than 0, right? Hopefully that logic makes sense. So where is our graph greater than 0? So when I look at my thing here, this is 0 where my mouse is moving. My graph is less than 0 on these arms because it's going down and getting into the negatives. These numbers are all clearly less than 0. I'm greater than 0 up here, and I'm equal to 0 on these black dots. So that's from 1 to 5. All right? Between 1 and 5, my graph is greater. And at 1 and 5, I'm equal to 0. So I can say my solution is from 1 to 5. Roger that. So if I were to sketch this again, here's my 0. Here's my graph. And from 1. Whoops. It doesn't really matter. I already showed you. Does this matter? Probably not. What the heck? So from here to here is our solution, from 1 to 5. Again, when it comes to Desmos, just plot one side and plot the other and then think it through. Okay? Say it out loud, think it through, take a look at what you're looking at. So this is saying, again, I can rewrite this as x squared plus 5x plus 4 is greater than 0. So you're asking yourself, where is this graph bigger than 0? To be bigger means above. So where is this graph above 0? Which parts of the graph are greater than 0? In other words, which parts of the graph are above 0. So when I look at my graph, I've plotted it, and I've plotted 0. Which parts of my graph are above 0? Here's 0. Which parts are above? These arms that are sticking out. So it's starting at -4 and sprouting out. Starting at -1 and sprouting out. Are these guys included in our solution? Well, if you look back at our problem, it says simply greater than, not equal to 0. So at those points, I'm equal to 0. They're not a part of my solution. So you would have an open circle. So I'm going to just do the roughest of sketches again. So here's my sketch that I made. So I'm not actually including -4 or -1. I'm simply starting there and going up. Starting there and going up. These pieces are above 0. Therefore, they're greater than 0, as it says. So I would write those two solutions as -infinity to -4, not including it. So, whoops, parenthesis, and -1 to infinity. To be perfectly honest, I know I've said many a time that, you should be comfortable solving these the other ways. But when it comes to inequalities, I would encourage you to use a graph, right? I'm honestly not going to sit here and stress about how to solve these algebraically. I don't know if that makes me a bad teacher, if I should stress about it more, but I personally think that an inequality makes more sense on a visual scale than it does solving it by hand. I will solve one by hand here, but I just think it makes more sense on a visual scale, like I said. So the tests. Oh, I gotta remember how to test it. So you remember how we were doing like the things where we would find the solutions and then we tested it? Didn't we do that? Or am I like mixing up last year? That'd be weird if I was mixing up last year. Pretty sure we did this. So I'm gonna look at this and I'm gonna solve it as if it said 0 for a half a second. Okay, I'm gonna solve this as if it said 0 for just a split sec, and I'm gonna use my B method. So like I've written it a million times: b over 2 minus u, b over 2 plus u. Okay, I'm not good. I'm just gonna scribble it. I don't think I need to write that down for a millionth time. So -1 minus u, because b is -2, so half of that is -1. -1 minus u, -1 plus u equals c, which is -15. So I'm going to get 1 minus u squared equals -15. And I'm going to get u squared equals 16. Take the square root, u equals 4. And when I plug that in here, -1 plus 4, -1 minus 4, I get 3 and -5. So this factors into x plus 3, x minus 5. So these are the zeros. The zeros are at -3 and 5. So let me kind of do this algebraically and graphically. So what we've done here is factored it like so. We factored it into... Why is my iPad frozen? Why can't I zoom in right now? Give me a sec. There we go. So we factored it and found our two solutions, our two zeros, right? Those are if it were equal to 0, we just found our solutions at -3 and 5. We just found them, right? I've been solving problems like this over and over, right? Those would be our solutions, -3 and 5. Because remember, it's always the opposite of those numbers. So I got a +3 and a -5, but then we turn around and have the opposite solutions at -3 and 5. But what we're going to do now, algebraically speaking, is test these values, which I feel like we did, but I could be mistaken. I could be losing it. We're going to test these values. We're going to test the number over here, test the number over here, and test the number over here. If our solution is less than 0, that part counts. If it's greater than 0, it's broken and doesn't work. So think about this. Let's plug in 10. Right? Let's plug in 10. So 10 plus 3 is 13, and 10 minus 5 is 5. 13 times 5, who cares what 13 times 5 is? 13 times 5 is clearly not less than 0. So this part doesn't count. You see what I'm getting at right there? I'm testing out a number and going, is it less than 0? No? Okay, that's not a part of the solution. What about in the middle? Well, let's plug in 0. That's an easy number to plug in. That's in the center. So 0 plus 3, 0 minus 5. I get 3 times -5, which is -15, which is less than 0. So this part does count. And then I test the number out here. How about, say, -4? -4 plus 3 is -1 times -4 minus 5 is -9. The two negatives become a positive. That's not less than 0, so this part doesn't count. What am I doing there? Graphically speaking, I'm testing a random number like 10 and going, oh, I got a positive. Oh, 10's way out here, I guess. That's the y value of 10. I plugged in an x value of 10 and was like, what's 13 times 5? I don't care, but it's something positive. Yeah, it is. So what I've just determined is that this arm from 5 on up is positive. And then I tested a number between -3 and -5. I tested 0. And when I plugged in 0, I got -15, which is less than 0. So I'm like, okay, so the middle is less than 0 because it's below this line. And then I tested a number on the left. What did I test? I tested -4. And when I plugged in -4, I got +9. Where's that at? Right there. We can barely, it's right there. Right there. It's right there. You can see it, right? I got +9. And so it was positive. So that part doesn't count either. So I just did a quick algebra test, right? I'm not seeing the graph, but I'm going, okay, what happens on the right side? What happens on the left side? What happens in the middle? And these are the zeros, so they are open circles, right? We don't want it to be equal to 0. We want it to be less than 0. So my solution is -3, oops, not including it, parenthesis, -3 to 5. I hope that makes sense what I just did. But we're practically imagining a graph with this number line, right? This is my right side of the graph. This is the middle part of the graph, and this is the left side of the graph. And I'm testing it to go, oh, is it above? Is it below? I'll do another one the same way. So 7/2 minus u, 7/2 plus u equals c. 49/4 minus u squared equals c. Subtract the 12, which is 48/4, which is 1/4. So take the square root, I get 1/2 for u. So 7/2 minus 1/2, 7/2 plus 1/2, I get 4. No, I don't. I get 3. And this one's 4. So x plus 3 times x plus 4 is greater than or equal to 0. So my answers that I get here are -3 and -4. And I'm plotting those, right? If this was an equal sign, I'm rushing through this because I've done it a million times. If this was an equal sign, I would do my U method. I often encourage the U method, and I'd get these two solutions, -3 and -4. And if you plot it on Desmos, you would see that, right? But it's not just equals to. It's greater than or equal to. So let's test some numbers again. So these guys count, right? Those guys are a part of the solution because they're equal to 0, right? Those are the zeros. And we want greater than or equal to. So we know the equal to part. Where is the graph greater than? Well, let's test out some numbers. If you plugged in 0, what would you get? 0 plus 3, 0 plus 4. So 3 times 4, that's 12. Is 12 greater than or equal to 0? Yes, it is. So this is a part of our solution. Now, theoretically, could these guys potentially be a part of our solution? Yes. Oh, I just realized I plugged in 0. This is not -3 to +4. That's -3 to 4. I plugged in the wrong number. You realize that? That's my bad. I was thinking this was a +4. It's a -4. So what's a number in between those two? Like -3.5. All right? -3.5 would be in between those two. That's my bad. So plugging in, so -3.5 plus 3 gives me -0.5, and -3.5 plus 4 gives me +0.5. Well, a negative times a positive gives me a negative, and a negative is not greater than or equal to 0. Again, what am I doing in here? I'm testing out numbers, but what I'm doing, which is again why I honestly do appreciate the graph on these. I really do. I would 100% encourage a graph. What I'm essentially doing is I'm testing out the number -3.5 and realizing, oh, it's gonna be negative down here, right? That's what I'm realizing. What I was just doing on paper, I'm testing this point out and I'm going, oh, it's below, so it's less than. That's not a part of my solution. I want to test some numbers out here, -2 and -5, and realize, oh, it's positive. So again, I'm honestly a fan of looking at a graph. So what we're going to realize is, oh, this is positive. Oh, this is positive, and this is negative. So these guys are out and these guys are in because they're positive. They're above and we want greater than. That's what we're realizing here by plugging in these numbers. So that's -infinity to -3, including the -3 and -4. I just realized I wrote these backwards. This should be -4 and this is -3. To positive infinity. And with that, I think I'm basically good. I think you probably get the point, but it doesn't take me that long to type in one more of these. So if you need one more, keep watching. If not, we're good. So I just plotted this guy right here. And what is this saying? We want to know, when is the graph less than or equal to 0? So I'm just going to look at a graph, honestly. Here's the blue graph. Let's imagine what would have happened if we did this by hand. We would have solved and got these two answers, 4 and 7. And then we would have said, okay, let's test 3, 5, and 10 and see where is our graph actually less than 0. When we plugged in 3, we'd get what? When we plug in 3, we'd get like 4. All right. And when we plug in 10, we'd get whatever clear up there. And we'd go, well, that's positive. That's bigger. That doesn't work. And we plug in 10, oh, that's positive. That's bigger. That doesn't work. And when we plug in 5, we'd get what? -2. And we'd go, oh, we found a negative. So, oh, it's less than 0 right here between 4 and 7. Why, yes, it is. You can clearly see that the graph is less than 0 from 4 to 7. And that's my answer, right? It's less than 7 from 4 to 7. Is it equal? Where is it equal? At 4 and 7. So they are included. And with that, I think we're done. I'm just going to end it right there so I can get that replay out. Call it a day. I'm kind of tired. Gonna relax. I'll see you later.